In this era of IT and IoT, the practice of architecture has undergone a phenomenal transformation. Lord Norman Foster, a British architect and urbanist who turned 90, is a key figure in the modernist high-tech architecture. Foster plus partners have done exemplary buildings all over the world. Foster plus partners is one of the leading architectural practices that pioneers in the application of computational design, data science, machine learning and artificial intelligence in the architectural design process. TSIGKARI is a senior partner with Foster plus Partners. She heads ARD, Applied Research and Development, a group pursuing state-of-the-art research in computational design and architecture, from complex geometry to machine learning. Her academic background extends from architecture, engineering to computer science. She is a specialist in performance-driven design and optimization, interfaces and interaction, design to production, stakeholder feedback and integration. Her work includes developing simulation tools, integrating processes and physical interfaces. In the past 2 decades, her work has contributed to solutions for hundreds of projects. She also teaches in University College of London, Bartlett on the subject of computational design. Her recent speech in Young Architects Festival at Mahabalipuram Chennai in 2025 is a comprehensive masterclass on applied research and development in architectural practice. Hi, this is Architect Venkatesh Babu. Welcome to Archidesign Talks. Here we talk about anything and everything related to art, architecture, environment and design.
Digital twins, optimization, and AI. But the question that we ask ourselves every single day is what technologies exist out there that can help us completely reshape our industry today? And I always like to say that technology is, after all, such a charming underminer of our own certainties. It constantly pushes us outside our comfort zone and forces us to rethink everything that we have been taking for granted. And so, in many ways, it is the white rabbit of our industry, a little bit like Alice in Wonderland, if you've read the book, where Alice follows a rabbit down a tunnel, and then all weird and wonderful things come true. And just like Alice, we can either choose to ignore technology, or we can go down the rabbit hole. And down there exists a lot of uncertainties, unknowns, and failures. But there also exists a lot of possibilities. And possibilities with technology is a wonderful thing, because architecture is not a single man or woman game, it's a group sport. We have a lot of different disciplines, a lot of different people working together to produce something better, but usually we're all in our own silos, understanding only a particular aspect of what we're trying to design. And in that way, it's a little bit like the parable of the blind man and the elephant, that I think it's very well known here in India, where we only judge things from our own experience. But I think technology is going to be the great integrator in architecture, allowing everybody around the table to deeply understand what everybody else is doing and change the game altogether. Because when we design a building, we have a responsibility of creating always something better than what has come before. And if we're going to look at everything that is out there and we're trying to build something better, then technology has to be an intrinsic part of how we operate. And I will give you a simple example of 13 St. Mary's Axe, London's first ecological tall building and an instantly recognizable addition to the city skyline. The building is rooted in a radical approach technically, architecturally, and socially. And this being quite an old building at this point, many people know that it has been developed by an array of different simulations that were revolutionary at the time and helped us shape the form of the building. But very few people know that it was Excel that made us and allowed us to do it. Given the lack of affordable parametric tools at the time and extremely limited interoperability between different CAD software, what we ended up doing was develop all our equations in Excel and write a small software in Visual Basic at the time to generate the entire building in our modeling software, which meant that any change that was required by structural engineers or our designers could directly be replicated through numbers into a model. So you see, we have been taking technology very seriously for a long time now. What you see on your screen is a picture taken 20 years ago, and it shows Arthur, which was an augmented research, or project around augmented research reality undertaken with University College London. The hardware that you see on the screens with the computers that supported it costed £100,000 per person at the time. But it allowed for fully immersive collaborative design around different players. So they would wear the headset, they would see the virtual design, and they could change it with these wands. So the ideas of everything that we wanted to do was already there 20 plus years ago, but the technology was not yet widely distributed or even cheap enough for us to use. But because we investigated the possibilities of this technology so many years ago, today we are able to use augmented and virtual reality not just as a visualization tool, but as a design collaboration tool and at a fraction of a price. That allows us to work with each other in many weird and different ways, and this sort of connection with each other is important because human collaboration between creative minds is at the heart of how we operate in the office. And of course, as technology evolves, our tools and the way that we work evolves as well, from very basic headsets. Now with gaming engines, the game has completely changed, and it has allowed us to develop applications that work a little bit like Minecraft in steroids, where the designer can not only design, but also analyze in real time all their options while collaborating with each other in an array of interfaces, from a normal computer, a touchscreen, or even VR headsets. And so, with that small introduction in what we do, I would like to start by presenting a few projects and how complexity and technology work together to create something of what I think is an interesting and a beautiful experience. This project would go from small, medium, large to extra large, and then the one that got away. So, let's start very quickly with the Vatican Chapel at Venice. The Vatican Chapel was something that was given to us in 2018 to draw. It was a Norman Foster project, and it was in a very tight time frame, and the space constraints were also very difficult. And so it allows us to have a completely different take on design to fabrication. It started with a kit of parts, which were timber slats, metal tension tubes, and fasteners. And then the orchestration of these elements introduced the complexity of the project. So we're not really talking about a very complex geometry, but rather the complex orchestration of the geometry. In the Pavilion of the Holy See, we cannot really point at a single element and describe it as complex. But the chapel as a whole and the constraint it needed to accommodate certainly were. The original design concept was to drape a thin fabric over a tensegrity structure that was made across 3 different beam crosses. It was a column and beam cross, and you can see it in the center, that there are 3 of them. But then at the very latest stage, it was decided the design to change altogether and to clad the structure in timber instead. And the idea behind that was weathering of the timber and how the growth of the surrounding vines would integrate the chapel and its landscape. So we worked closely with the design teams, the fabricator who was techno, and the structural engineers, and in a very tight time frame, which was around 3 months, we had to do all the different design variations to do the fabrication and the installation on site. And you can see here the interleaving of the timber slats which was both a structural necessity for the stability of the pavilion, but also a fundamental pattern of the design. Our parametric model had to account for precise positioning of the timber cladding elements in response to various changing structural models. And this positioning affected the length of each timber and the points that the timbers were fastened with each other. So that was really significant because that was when the tension tubes were connected. And in that sense, precision was really critical because we ended up delivering construction drawings and dimensions directly to the fabricator from our model. So through this one parametric model, we have everything. Every change is replicating the model in real time creates the documentation, which is construction documentation, and that construction documentation, which is automatically created, goes to the fabricator. So every change is replicated in real time, and details were very carefully considered to facilitate assembly on site. And you can imagine everything is based on that one model that we need to check all the time. So we ended up writing a small software that did direct class detection as we were designing. So even very small collisions of the millimeter could be directly spotted on before anything went really bad. The result of this precision modeling and documentation provided a rational structure for the beautiful randomness of nature as the pavilion cladding has become a trellis for the vines planted around it. My medium project could not be but something here in India because we do a lot of work in India and I couldn't have a presentation here without showing you some of the work that we do. That is the D.Y. Patil University Center of Excellence, and it is a really wonderful project. I spoke quite extensively with Chris Bubb, who's the head of this project. And he always tells me that in this project, technology is not the master, but the server. It's a combination of a passionate client and a very strong drive for performance-driven design. And it was really technology that ensured us that we analyze every single aspect of the design to make sure that the building worked appropriately. On your screen you see a typical floor plan that was fully adaptable, and that plan kept changing all the time, with a very focused point being on the light wells, and the light wells were the center of a lot of different activity because the light wells are actually quite adaptable. So different light wells can be used for different uses and can adapt based on different needs, and that was a very big characteristic and is still a big characteristic of this building. We keep talking about performance-driven design. What does it mean? It means that you're trying to create a building that performs in relation to your experience, trying to make your experience the best it could be. This is a very good example for the gardens. The gardens were actually analyzed extensively against light, temperature, sound, and air to ensure the more comfortable experience when it comes to that light, not too much humidity, allowing for subtle air to come in and create natural ventilation, etc. So a lot of these choices, although they just seem and feel right, they're not random. They're very carefully thought beforehand. As I said, sustainability is very important for us, for every building that we do. And in this case, the university has a LEED Platinum accreditation, which is as high as it gets. And that's because, despite this being a concrete building, something very clever was done. When we have concrete, it's cement usually that has the most embodied CO2 and creates most of the sustainability issues. In this case, what was done was that 60% of the cement was replaced with GGBS, and GGBS stands for ground granulated blast furnace slag, and that is a byproduct of making steel. And just by doing so, we have concrete that embodies far less CO2, while in the same time is cheaper and looks whiter. In continuing trying to explore sustainable ways of doing things, I will show you how we work through the facade to ensure natural ventilation. But what is also important is how we manufacture these things. So in this case, we started by really looking manufacturing with a very local manufacturer who created these rubber molds that could create the performative facade that we were looking for. Unfortunately, this facade as it was and these molds did not work or perform exactly as we wanted. So we moved on to a different idea. You see here how we analyze the facade, and you see that the facade needs to provide natural ventilation and light throughout the day, but in different levels based on the use. That means that depending on your orientation and the use within the building, the facade will be different, even depending on the height. So in this case, you see 4 different facets of this facade, and you can see an average illuminance of various luxes. But the difference is that the first one allows only 15% of the maximum luminance to come in, while the latter allows 28%, because the first one is a stairwell and the latter is an office. And the entire facade is really sculptured, because again, depending on the orientation, how these cuts are being done, where it allows light to reflect or be stopped or get in, needs to change as well. And you can see interior and exterior view. At the end of the day, the manufacturing was with a very ingenious design that incorporated wooden molds and perspex, if you believe it, and that created this type of prototypes that I think look really, really wonderful when on site and give this building this constantly ever-changing feel as we go about and we explore it. So we have a low-tech, high-tech solution where we used everything in our means to create the most appropriate experience, and I think whoever goes in the building say that it just feels right. We'll move on to China Merchants Bank headquarters, which is a project with a complex and very beautiful geometry that was inspired by traditional paper folding and rock formations of that region. The team were tight in time, but yet they had an abundance of ideas around design to do a lot of 1,000 and more different things every given week, all while coordinating with multiple stakeholders and in a very, very short time frame. The tower's facade is made from glass and stainless steel and is the result of an iterative process that was trying to minimize the energy consumption of active systems within the building, and it was trying to do that by carefully balancing and controlling solar shading, daylight, and thermal loads. The tower actually achieves 3 stars in the Chinese assessment standard for green building, which is the highest rating available for such a building. So, you see here all the models, because what we have is a very complex project with multiple stakeholders, with a lot of different models to coordinate. So here you just see the grid and cladding model, environmental model, structural model, mechanical model. Each of these models change, all the other models have to change as well, right? So you can imagine if this is a linear process, one single change can take a long time. And this needs to happen in a very small amount of time with a very small team. And so we saw it as a project that negotiates as much geometry challenges as coordination and workflow, and that's something that we really wanted to focus on, how we can make this workflow more efficient. And to do that, the first thing we did was draw a data flow diagram that really could allow us to understand who actually owns what data and how that data flows across the process. From there, we start building parametric workflows to automate different aspects of the project delivery, and not just automate, but allow for changes in one model to happen simultaneously in all other models for every other stakeholder. And we managed to do this by using our proprietary interoperability software called Hermes, which we're going to show you in a bit. So through these different models and these different workflows, what we managed to do is an array of different things. We allow, for example, for Rhino files to directly deliver Revit adaptive families. So you go from a Rhino parametric model to an actual BIM model that is fully adaptable as well. We allowed for a lot of metadata diagrams to be created, and we allowed for different stakeholders to only ever retrieve the type of information that they needed. In this case, you see on the right-hand side data on demand used by an environmental engineer, where they don't want to analyze usually the entire model. They want to analyze every 2 floors or every 3 floors. So through that, they could just select the levels they wanted, click a button, get that model directly within their own software. In addition, things like that happen with the structural engineering teams as well. This video shows you how the team works. So the structural engineers have 4 types of columns and they need to size them differently. And every time they run different analysis or the model slightly changes, that sizing changes. And that sizing is driven through the Excel spreadsheet. That sizing then affects 16 different cladding variations around the columns. And those cladding variations do not only depend on the typology of the column, but also on the location of the column on site, as well as the relationship that it has with the facade, which is also changing based on the location. What we're doing here is the structural engineer is changing the sizing of the columns in Excel. That directly creates and is being pushed into the parametric model by just clicking the Hermes button. The entire columns, everywhere that these columns exist, update. All the cladding gaskets update, and the entire geometry adjusts to that new column size. So this happens literally in real time as you see it on the screen. And so that's a direct connection between your structural engineers and your designers. That doesn't have to do with an export and import, etc. Another challenge that we had was that we had to create a blueprint for this. It was not enough to just send a model. We had to send a way of thinking, what we call a geometry method statement that allows anybody with any knowledge whatsoever to take that method statement and recreate the model without necessarily having to have all the computational knowledge that we may have. And we managed to do this by splitting also the geometry in different parts that are the same. And the geometry statement that you see there was also automatically created, not manually created. The only manual part from this geometry statement is actually the translation in Chinese. Another thing that we played with in this tower was physically accurate materials. And for those of you who don't know, physically accurate materials are materials that allow you to closely resemble how light interacts with real-time objects. So we use physical-based rendering for this exercise, and we did that through a software called Omniverse from NVIDIA. Omniverse allowed us to, again, push different information from different people in one single platform, and we wrote a few programs that let us change these materials in real time and change how the tower looked. And we went for this idea of a digital mock-up. You know, you have to create physical mock-ups that cost not just money, but embodied CO2. You have to travel a lot, there is a lot of money in creating them and traveling to see them. So we were trying to avoid doing too many tests with physical mock-ups. So we said we're going to do it digitally. And the result was the top right-hand corner image. And when we showed that to the design team said, there's no way the glass is going to look that black and the entire thing is going to look black. Lo and behold, the bottom part is an actual physical model. Do they look the same? I think they do look considerably the same. So through that software, we can do digital mock-ups very, very quickly. And here you see on the left-hand side of each one of these pairs of pictures, you see our color-corrected render delivered through the software. And on the right-hand side, you see the original photography of the tower. And I would say that they look pretty similar. Imagine how much sustainable you can be if you don't need to create 20 mock-ups, but just the final two. And so there it is in all its glory in a rendering, but soon with you as it has topped up in April 2024. For those of you who don't know, Mahabalipuram is alive again. It has been announced in November, and we do have tender for 2 buildings. And for those of you who don't know, which I think there are very few in this room, this is the new master plan for the new government complex of the administrative capital of the Indian state of Andhra Pradesh, and it's a 270 square kilometer city. And the project includes the design of 2 key buildings I will talk about, the Legislative Assembly and the High Court complex. Measuring 5.5 kilometers with 1 kilometer width, the governmental complex occupies the heart of the city, and that's where our main design work in terms of master planning. And it's defined by a strong urban grid that structures the city around it. A green spine is running throughout, and actually 60% of the area of that grid is not buildings, but it's occupied by greenery and water. The high court complex is located on the central axis, and it has a stepped roof that was inspired by India's ancient stupas. And it has been influenced by traditional temple arrangements. Today I had the good luck to be taken to some of the ancient temples that you have here, and they were wonderful. And Raja, who so brilliantly kind of toured me around, he was explaining how you have this concentric circulation and rooms that follows the temple, and that's exactly what we have here. We have concentric rooms and circulations around the entire building. And we also have a courtyard and a roof garden that allows the greenery to penetrate into the interior spaces. And the deep overhangs of the roof provide shade while also providing natural ventilation. That was very important because we wanted a canopy that would be fully comfortable almost throughout the year. We achieved that by trying to be very sustainable. The entire city has been designed to the highest standards of sustainability with the latest technologies that are currently being developed in India, like photovoltaics. And in this case, the roof opens up, it allows for air to come in, and so it can be fully comfortable and airy and not too hot and humid. And the PVs on the top gather so much energy that allow for the building to run all year long just from the PVs alone. So this exterior space we analyzed, and we have found that the exterior space has enough comfort in terms of temperature and natural ventilation for somebody to be there and stay there for 11 months a year. And the only month that is actually too hot, and even these measures cannot help you if you don't have technical ventilations, which we don't in these spaces, is the month of March, which I understand is the hottest month here, or I think May or March, one of the two, May. And so for that month, the courts are also closed, so it's going to be okay. At the center of this green spine lies the Legislative Assembly building, which I think is quite a democratic and cultural symbol for the people of Andhra Pradesh, or has the potential of being. The assembly sits within a large freshwater lake and is framed by the Secretariat and other cultural buildings. And inside it has two major debating chambers and a lot of admin facilities. But what I find really spectacular is the spire. This idea that the parliament is under one roof and you have a spire that's walkable, and the people can actually go and look what happens underneath. So it's a very, very symbolic thing that you, the people, have control over the parliament in many ways. And it reminds me also of what has happened when we did the Reichstag spire and the dome. And that is very, very powerful. So I hope that this will become the symbol of a new city. When it comes to projects, I will finish with the one that got away. What could have been the Mexico City Airport, a 1.6 kilometer long space frame, and an incredible challenging project due to an array of constraints. Let's begin with structural consideration. The entire city of Mexico used to be on top of a lake, so the ground settlement conditions are really horrific. It's a highly seismic zone, and you've seen this, the earthquake that happened a few years back that was devastating. And to top everything, we had a volcano nearby that every time it kind of exploded a bit of ash, that was volcanic ash that when wet, it became concrete. So quite a few interesting challenges to deal with. Now, in terms of sustainability, we have a roof that works really, really hard. It has to integrate not only structural efficiency, but also thermal performance, ventilation, glare, daylight, and views. But most importantly, we're trying to rethink the paradigm of what an airport is. We want something that works as one single skin, lightweight and continuous as an envelope. And something that also did not distinguish between wall, ceiling, and column. And to do that, we went to previous work that we have done in space frames. You may recognize the British Museum Great Court Roof, which was a space frame that we developed as well. And it was also a famously hard one to solve. And the difficulty lies on the transformation of the space frame from a rectangular boundary on the edges to a circular boundary in the center over a double curved roof. Now imagine that this roof is only as big as the 21 funnels that we have. In terms of scale, we're 90 times bigger. In terms of topological complexity, we're thousands of times more complex. So, how do you solve a problem like that? I think the way we did it was with this idea of divide and conquer, where first we defined the topological connectivity of each one of the hundreds of thousands of nodes we had on our space frame in 2D. An alien is coming. And then we pushed each node up based on a mathematical equation where we thought would be its right position before dynamically relaxing the entire thing to find its optimal shape in compression. What you see on your screen is the formula, the mathematical formula that created the initial 3D model from the 2D configuration. And then this is the dynamic relaxation that we run, so it's a really mathematical defined hanging chain model, which is exactly what Gaudi did with Sagrada Familia to calculate its volts, but in a digital format. And all this is just scratching the tip of the iceberg, because from this we have to create the tetrahedron mesh, all the models. Like I cannot even start to explain the level of detail that we had to put in this model that created a finally BIM model so complicated that it was showcased in the Royal Academy in London as a piece of art. And just to prove that this was actually happening before it flooded, this is me on top of the funnel overseeing like our beautiful handiwork. Yes, the dream may not have come true, but what was and still remains true is that with this project, like with every other project, we are trying to create a fantastic experience. Because as architects, all of us, I don't think we're creating buildings, but we're crafting experiences. We wanted to create an airport that was welcoming, bright, lightweight, singular. And what is more interesting is that a lot of people that looked at the airport and seen that movie, even when we saw that movie, we were like, this seems so simple. Like, what did you do? They kept asking us. That is so complicated. Everybody says that this is such a complicated problem, such a complicated project. But it really looks simple to us. And I always like to say that this is always our bigger achievement, that we make really complicated things look effortless. But I promised you technology, and I showed some technology, but not too much technology, so here it goes. And if you feel the urge to leave, I would not be offended. We discuss about technologies in architecture, and everybody discusses now about BIM as if it's the height of sophistication. And I would say BIM is in the past. What is in the future are technologies that can reshape our industry, and these technologies very rarely come from within the architectural industry. They usually come from the games industry, the movies industry, or even computer science industry to revolutionize the way we work. And I will start with GPU computing. For those of you who don't know, it's the computing that happens in your graphics cards, right? And this type of computing was predominantly developed to accelerate computer graphics and to initially allow for real-time interaction in games. For those of you who were gamers, you remember the games in the 80s and what you saw, and you can compare it with games right now, right? But if you take GPU computing in architecture, it also has the potential to revolutionize performance-driven design in our industry and make it something that was an affair of hours or day to a real-time experience. Key to performance-driven design is this real-time feedback, is the idea that you can create something, and as you create it, you can directly see whether it performs or not, so you can change the design and you can check what you're doing right. And this is what tools like our in-house Cyclops do. How was Cyclops created? Many years ago, in 2007, we needed to create something that allowed us to visualize what we can see from every single seat of a stadium. So we were running views from every seat in a stadium, making sure that every single seat was great. At that point, we could run around 24 views per minute. But today, by just using the computational power available to us through GPU computings, we can run more than 600,000 views per minute. simply by taking advantage of the GPU powers in our laptops. This means that we can now run anything that is related to ray tracing, so daylight, sunlight hours, views, artificial light, not in a matter of days or hours or minutes, but in real time. And do that on not just a building scale, but a city scale. And therefore our designers can now very well understand how their options perform as they create them. As I explained before, GPU computing is helpful in different ways. In using gaming engine software, we have developed tools like Thalia. And Thalia works a little bit this Minecrafting steroids idea where you as a designer can start designing something, and as you design, you can get back feedback in real time against all the errors that you're creating. How well your daylight works. What is the simulation in terms of whoever works in your floor plates every given time? What is the financial ROI? As these key performance indicators can be directly connected with your design changes. And we find that platforms like this empower designers to calculate and compare these key metrics for their options in real time, and therefore allowing them intuitive yet informed decision making very early on in the design process. And with that in mind, that's how we created our new carbon calculator. So this is a tool that let us, even from sketch design, to be able to very quickly say whether a solution is better than another solution when it comes to good carbon. And we work with that not just in terms of materials, but different uses and also different typologies of structure, because we know that Foster & Partners may create things that are more complex or difficult, and we need to take that in consideration when we're doing CO2 calculations, because we don't want to undermine how important this is. Another capability that first thrived in the visualization and film industry before being introduced to ours is distributed computing. So cloud computing or computing through different cards within your office. So by moving distributed computing from faster image rendering, which was initially what it was created for, and I used to go to conferences like 15 years ago where everybody was saying, how can I run a really good high-end analysis, not in 3 days, but in 3 hours. That's how this was developed. If we take that, therefore, from image creation to actually analysis, then we can turbocharge completely our optimization capabilities. And by optimization capabilities, I talk about this idea of using genetic algorithms in the design process, where you're specifying the design DNA that describes what you want to design, so basic characteristics and parameters, and you specify the objectives. Do I want it to have good daylight? Do I want to have views? Do I want the area to be a particular type of area? And then you allow the computer to work it out, and the computer will create a lot of different options in order to produce something, like in this case in this tower, options that say what would be the tower's massing if I wanted to have the optimal views to the Petronas Tower, this is a tower in Kuala Lumpur, but also keep having structural stability and daylight. But what happens when you try to apply these sort of premises on a city scale? And I will show you Guangdong, China, which is a good example of that. That was a winning competition that we did, where we used our in-house distributed computing system called Hydra that allows exactly for that. So with this project, we were interested in developing from scratch an urban layout that maximized connectivity between the different neighborhoods, views towards the central hills, daylight potential, as well as total floor area. And we could spend months and months creating and analyzing thousands of options to find the best performing ones. But instead, we fed the requirements and design rules to the computer and allowed it to do the heavy lifting for us. The genetic algorithm that we used actually generated and evaluated a few hundreds of thousands of options, and at the end it gave us the 100 best options from which we could start working from. And we could also have an interface that would explain to us why an option was better than the other against the criteria that we set. And that is not something that took us 3 months or 3 weeks, but we did those hundreds of thousands of options overnight. To compare options, we also create different web applications, because again, this is not the design. We're not using these things to produce a design. We're using this to help the designers find the best solutions. So this is something that we then give to the team, and they say, okay, after all this exploration, these are 100 options that comply with to your satisfaction to the objectives that you set. Go to the web application, see every option, explore it, understand what makes it better for daylight. Where is the massing sitting to make it for a better solution? And then, just because we can't create a PDF report that you see on the right-hand side, which is a one click of a button, to also explain to the client why this is better, and then start working from that option to create these magnificent designs that is a Foster & Partners design. Moving on, technology not only helps us design better, but also better connect with each other, whether in terms of software or in terms of experiences. And in terms of software, interoperability is key. And I've already spoke about Hermes and how it helped us. Just to recap, Hermes is a cloud system that facilitates the exchange of design data in real time across different people working in different software in different locations across the world. And so this not only better connects design amongst all stakeholders, but also permits substantial changes to happen late in the process. And that was very true for the Lusail Towers that we've done in Qatar. It was commissioned in 2019 to be ready to build by 2022 for the World Cup. And there were only 9 months of design time with substantial changes in the design during that period. And the height of those changes were that a week before we delivered, the client decided to drop the tower by 10 floors. Now, the way this tower is created, and there is my colleague Marius Iliakos, who worked on the geometry of that, has a 1.5 hour presentation to explain the complexities of the geometry itself. It's not just about chopping 10 floors, the entire geometry needs to be reconfigured. But because all the different disciplines that you see around the table were connected through the software, a design change meant a change in the MEP model, meant a change for the environmental sustainability engineers, meant a change for the structural engineers, happening simultaneously. So we dropped the model, the parametric model, sorted this out very, very fast, and that change propagated throughout everybody to do the analysis and be able to complete the regeneration within the week and deliver the design for these wonderful towers that are now live, and the detailing on the cladding itself is really worthwhile to see. And I mentioned before collaboration, about collaboration of software and people. When we come into people, I think, and an experience is the design experience, and the way that we have to share our design experience while collaborating is a very significant part of the design process. And that is where we find that extended reality, which XR stands for, so both augmented and virtual reality, is yet another technology that came to revolutionize the way we work together. Our team has 20 plus years of experience in extended reality, from stereo projectors to iPads to the first Oculus headset, for which we've been at the Kickstarter before it even came out, which meant that during COVID, when we were all at our houses, we could do things like that. So what you see on your screen are two of my colleagues, Zahan and Sharon. They all see the house of the people who's on the back of the headset from which you see the video, which is Khaled, and they're doing a review using multiple media, from kind of digital 3D models, movies, sketches, and they can all do that from the comfort of their own house. And through these experiences with extended reality, we developed again another software in-house called Glaucon, which allows us for on-site review processes like planning, applications like you see here that we've done in London with the planners directly, and also allows for immersive experiences and digital mock-ups to be very, very well received. And we found that the power of this technology to help us be immersed in a design has profound effects in the way we experience both space as well as collaboration with our peers. And as new hardware comes out, like Apple Vision Pro, we have seen, I'm sorry, I need to do this because as always it crashed. Yep, Apple Vision Pro, we were lucky enough to actually try Apple Vision Pro through Apple's headquarters and work with them 6 months before it was delivered. So that meant that we could apply things like that and allow for real-time environment lighting on-site at the city scale to be experienced in an immersive environment. So current hardware developments bring the reality of a metaverse much, much closer. And the metaverse is not something that Facebook and Meta invented. It was a term coined by Neil Stephenson in 1992 in his sci-fi novel Snow Crash. And it refers to a connected virtual experience of a digital space in parallel to our physical space. And just to prove to ourselves that this has some meaning, we created our own metaverse. So what you see on your screen is not a movie, it's actually a game. It's a multiplayer digital game that allows you to go through our office, experience our office, and not just our office, but go and jump into various different experiences with your peers digitally. Like, for example, go and see the top of 30 St. Mary's Arcs, go and check the campus and the digital twin that we have in the campus, go and check our materials research center with all the materials, or even experiencing Mars. And it has a lot more interesting things to show, but in the interest of time, I will move on. And I will move on from headsets to planes, so we're going into a scale change, because it was the aviation industry that introduced many decades ago the implementation of digital twins in their design process. And today, the architectural engineering construction industry has been fully adopting digital twins as a means of optimizing a building's experience for its occupants long after the delivery of the design, as well as feeding back to the design process itself. So at Applied R&D, we couldn't but jump at the possibilities digital twins hold, particularly for the development of smart buildings and cities. And to that end, we have developed our own Internet of Things toolkit, and on top of that, we built a smart campus application which connects our ongoing campus twin development. And through that, we can not only monitor and regulate how well the buildings perform within our campus, but most importantly, identify metrics that can positively affect the experience of its occupants and potentially train the building systems themselves to perform in relation to how its users want to perform. And in order to do our digital twin, the first thing that we have to do, go and create a three-dimensional model, and that is a point cloud that we have created for our office. And we realized that creating these point clouds is not an easy thing. Furthermore, what happens if you want to create many of them? And what happens if you want to fit them in the digital twin to see, for example, how well your construction works? And that's how Spot came along. So we were the only architectural firm to be part of the initial program for Spot, where we had the robot with us we were supposed to have it for 3 months, we ended up having it for a year and a half. And what we were trying to do was trying to bridge the gap between as design and as built. And so Spot will automatically walk through our building here in Battersea Park, and it will take point clouds that, through the help of a software we were collaborating with at the time, would create BIM models, and those BIM models will showcase the deltas between the as design and as built. And we'll start thinking then, can Spot actually start becoming part of an operational twin? If instead of putting sensors everywhere in that room, you have sensors on the dog who walks around the building and directly picks up things like temperature, how many people are in a room, how long is the queue for somebody who's drinking coffee. Can that fit back in the digital twin and allow us to very quickly change parameters and change the way the building operates? So these are some very interesting ideas that I think are going to become more and more common in the years to come. And I will kind of wrap this all up with AI and machine learning, because when we're talking about technologies that came outside the AAC but will have a profound effect in our industry, we cannot but talk about AI, which I think has the potential of bringing an unprecedented change at our profession. But as many of you know, change can have unpredictable consequences. Think of the iPhone, a technology nobody even knew needed, but nowadays not only every one of you has a mobile phone, but that phone has also completely reshaped the way we socialize with each other, because it brought up the rise of social media. So what will the consequences of disruptive technologies like AI could be? what would the consequences of AGI could be? A term you might have heard, which is architectural general intelligence, a computer system capable of not just mimicking us, but generating new scientific knowledge and performing any task a human could. Before we reach AGI, if I ask any of you what you think AI is, I'm sure I will hear ChatGPT, Midjourney at the most, right? And it's true. Like through these developments, we had incredible technological advances, new foundational models. So big machine learning models that we developed have moved from simple image manipulation to natural language processing and content creation, right? We're not just processing words, we're creating things from words. So generative pre-trained transformers, which is the GPT of ChatGPT, are rewriting the book to IP, productivity, and I think also creativity. And on the other hand, you have what you know as Firefly, Midjourney, DALL-E, Flux, whatever it is, the flavor of the day, which are really diffusion models, which produce images like this by simply using natural language prompts. And most people think that that's it. That's where we are. This is fantastic. We can create images now through AI. Wow. But this is just the tip of the iceberg. Even since 2022, like 3 years ago, we have applications that have moved from images to creating movies, 3D models even, meshes, entire experiences. We're going into what are called multimodal zero-shot models, which are models that are trained against different modalities, so word, image, video, anything you can imagine. And they don't need to be trained. They need only kind of one expression and they will create things for you. So, will AI replace architects? It would be a good time to have a poll here and see what you think. But I would say no. I don't think that creative minds have anything to fear from the advent of technological revolution. And that the truth is that if we play our cards right, AI is not going to replace us, but rather augment our creativity and problem-solving capacity. Because whether you are a Peter Pan fan or a Battlestar Galactica fan, and I'm not sure I will have many in this room of either, you will know that all of this has happened before, and it will happen again. We're at a turning point not different to the creation of the printing press, or the splitting of the atom, or when it comes to our industry, the introduction of CAD software. But to harness AI's power, we first need to be able to control what powers it, and that is data. So our first point of order should be to collect, organize, and process our own data across disciplines, and in a meaningful manner in order to be able to leverage it in the future. And we have data across the entire cycle of a building's life, from design to construction to operation and beyond. So let me take you through some of these things and start explaining how these areas are transformed by AI today. We discussed before how through software like Hydra, we are now capable of creating, analyzing, and optimizing tens or hundreds of thousands of options, not in a matter of days or weeks, but hours. Now, just imagine, in a matter of hours, we produce thousands of solutions on a city scale, but also tens of thousands of analytical results that tell us how well these solutions perform. So, could we use these rich data sets to train the computer to predict optimal configurations, not in a matter of hours, but in a matter of seconds? And the answer is yes, we can. We can create generative design like that, and a lot of people and a lot of software are actually focusing on doing exactly that right now. But beyond generative design, there are many key areas where AI is expected to impact the field of architecture, and I will discuss a few of them, and I will show you what my team has done within Foster's since 2018, where we start working with these systems. The first thing we do in 2018 was create a design assist model that can be a real-time assistant and provide guidance for difficult problems in real time. In this case, we developed such a model in 2018 when we collaborated with Autodesk, where we used artificial intelligence to predict how a passively actuated material would react under temperature change. We then looked into surrogate models. Surrogate models are machine learning models trained on huge data set to replace slow analytical processes. We have developed such models for analysis like visual and spatial connectivity since the early 2020s. And in these cases, we have visual and spatial connectivity that tell us in a space how far you can see and how connected you are with every place, which is very important both for big floor plates as well as urban design. With these models, we are now having orders of magnitude faster prediction of what the analysis could be. And in this case, you can see a tool that can be deployed office-wide, where you create a floor plate, and then you click a button, and our ML inference API on the backend directly predicts what the analysis would be, which is 90 to 95% close to the actual analytical engine. Knowledge dissemination is another huge aspect of AI, particularly through the rise of large language models and these multimodal foundational models we discussed. Through those, we have developed and deployed office-wise tools like Ask Foster & Partners, an application that allows people to search our design guides that have been created over the past 50 years using simple queries and getting back instant answers. So you can ask something like, what is the best cladding that I can use for residential in India, and it will probably tell you. And we're now expanding that into different data sets. We have been writing prototypes to search through all our design details. We have developed prototypes that allows us to work through a material. So in this case, you can have an image, you can hover over the image will identify the element that you're picking, and will try to search what material this is from the data set of materials that we have in the office. And through using these tools, we realized that we really want to use these models in order to augment rather than replace our designers' creativity. And to do that, it's not just about image making. So in using diffusion models, we are now looking into taking the 3D model directly from our CAD software and creating suggestions of what this could be. And you see here something that was done now more than 18 months ago around diffusion models, where on the left-hand side is one view in Rhino showing the model, on the right-hand side is a real-time view again in Rhino showing some suggestions. But because these models developed so rapidly, 6 months after that movie, we were able to get results like this. So we are having again our machine learning inference API directly within Rhino, and any designer can design anything, write a prompt, click a button, and get a suggestion of how the design would look like. And we extended that to our AI portal, which is deployed office-wide, and it allows for people directly through Rhino to be able to create renderings, use different models, Flux, SDXL, Firefly on the backend, be able then to share results for cross-pollination across the entire team, because it works through SSO, so it's very secure and only works with people in the office, allows for branching of images, everything is hosted in our servers, so IP is not jeopardized. It also, let's see if that will work again, allows for automatic prompting. Most people who use AI find that it's very hard for them to write the prompt that will actually create what they want to see. In this case, for example, we can drag and drop an image to the prompt, and we can say, write me a prompt that will show me something similar to that. So the portal will write the prompt and will create the image for you directly. And now we're moving into movies, where we can also create movies through the use of AI through prompts. And to 3D models. So on the left-hand side, you can see a 2D image, and on the right-hand side, you can see the 3D equivalent image by just taking advantage of the new algorithms that are becoming available every single week. And we're using this for operational data insights as well, that I cannot go into too much detail, but it's really good for financial decisions. And yes, there are a lot of things around design, construction that I haven't spoke about, and operation even more, that can be revolutionized through the use of AI, and there actually are being already. And further to that, imagine what will happen in 10 years' time when AI agents will have taken over, and a lot of our process can be completely automated on the background. Will that mean that disruption will replace creativity? And I think that doesn't need to be the case. we can ensure that these disruptive technologies augment rather than replace our creativity, but we need to be careful of things like data contextualization and regulations, how we lose or not our IP, how education needs to work in this context, what are the unconscious biases that are embedded within the data we train these systems, what are the ethical considerations, and also what is the job upskilling that we need to do. What happens when we throw really bad data into the systems and we get really, really bad results, and that is a self-feeding system, and everything becomes completely the same and universally bad? Then we have data degradation and stagnation. What happens if we just use these systems and we completely lose domain knowledge and we don't understand a good from a bad solution because we were too lazy to really learn that, because a computer could just tell us what we took as an evangelical truth? And what happens? Well, potentially you have skill commoditization, where you have companies that are doing for you the equivalent that the IKEA kitchen creator is doing. So you go there and you say, I want the house so and so, and the system will create it for you. In a very possible and probable future, these are all possibilities. But I think that we can put our minds together to understand how we can better use these resources now. If resources will not be measured against our compensation, if, for example, you need somebody, you don't need 100 people and 3 months to do something, but you need 10 people in 2 days, how is then that benchmark against the value we have as architects? I think this is benchmark based on what we have and will always have, which is our creativity. And I want to always close with this idea of photography. When photography came along, everybody thought that this would be the end of painting. But that was not the case at all. What that was doing at the time was that it forced people not just to paintings that looked like photographs, but actually explore different means of painting. So could that happen with architecture? Could this be our photography moment? Well, maybe, I don't know. We live in interesting times and we're riding a very, very high wave. The exponential acceleration that we're facing is unprecedented, and I think the stakes are too high, but so can be the rewards, because technology has and always will bring change, but that's okay. We can only thrive by going outside our comfort zone. In fact, as Norman says, the only constant is change, and all we have to do is embrace it. So with that in mind, I would like to thank you for your time and patience for this very long presentation.